Good. Well, just let them all get their shoes and socks off. There's another benefit, of course. You can be very comfortable at these meetings, Melissa. You see, pints of beer, glasses of wine, all that. Yes. Good. We're starting to fill up a bit. That's grand. Evening, Dusko.
Evening, Doctor. How are you?
I'm all right. That's good to see you.
On time for once.
Absolutely, yes.
No excuse, really.
It's a lovely rarity. Hope everybody's fitting well at the moment.
Yes, I hope you're fitting well, Nick.
Yes, oh, hello, Dave. Hello, how are you? How's Welsh Wales?
I'm all right.
Good.
Family, oh well.
We'll be muting everybody eventually, don't worry. Yeah. Okay, well, we seem to be on time. People might start drifting in, but this is the 4th meeting of the year, and we're keeping going on a monthly basis at the moment. Good to see you all. Hope everybody's keeping fit and well. We've got the next meeting is our first telescopic topics. We haven't had a telescopic topics meeting for about 18 months, I don't think. It might not be quite that long, but this is going to be on the 10th of May, so a month from now. And anybody got short presentations that we can do via Zoom, so much the better. Dave and I will do something. But anybody else who's got short presentations would be fun. And then following that, our June meeting is Jens. Jens is with us tonight, Jens Bus, and he's going to talk to us about infinity, which is a fascinating subject in its own right. And Jens, of course, is our expert on somewhat difficult concepts made easy by himself. So that's grand stuff. And then we'll see how we go. I think I've got a nasty feeling you're being subjected to me in July, but we'll come to that nearer the time. Well, tonight I'm delighted to welcome a new face to the Natural History Society with Melissa Gillone, who is a PhD working in Birmingham, living in Stratford-on-Avon, so not so far. But she comes from Italy, as you might gather from the name, from near Turin. She got her degree at Torino University, or to be proper, I suppose, Torino. And she has been working in Birmingham as a research fellow and teacher, and has largely studied galaxies over the years. And although she's got a lot of astronomical interests with regards stellar evolution and cosmology, I think galaxies are probably her first love. And so we're delighted that Melissa is able to join us to talk to us about the most interesting area of galaxy evolution. So I'll hand over to Melissa and look forward to her presentation.
Thank you. Good evening, everybody. Well, I got introduced very well, so there's nothing more to add to it. One thing I would just like to add is, so I stopped working in Birmingham, and I've actually left the field at the moment because it was becoming too complicated. I decided to settle down, have a family, so I'm off. I'm off astronomy, unfortunately. I love talking about it though, so I keep on going around and doing talks. I'm in contact with lots of my ex-colleagues in different fields. I keep updated as much as I can, of course. I'm not with my hands in, but this is definitely what I've worked on. I've done my PhD on it, well, my thesis first, my PhD, and then my postdoc. So this is the topic of tonight. I hope it's not too boring. So first of all, I want to, wait. Okay, right. Brief overview. So I will follow these points. I try to give it logic. So I will start talking about galaxy properties, of which you probably know a lot, and then try to put the galaxies in the context of the large-scale structure of the universe, and then their environment, how we observe galaxies, how we observe distant galaxies, observations in terms of what we know so far, and then evolutionary processes, which is my topic of expertise, and then conclusion. I don't mind if you want to interrupt me because I'm not clear or anything like that. Otherwise, if you want to keep the questions for the end of the talk, I'm happy either way. Right, so first of all, a definition. So this definition was taken from the Oxford Dictionary, and it describes a galaxy as a system of millions or billions of stars, gas, dust, held together by gravitational attraction. What they forgot about was dark matter, which I added. So this is just the definition. So based on this, we'll start describing a galaxy. What do we see? Well, first thing we see is its morphology. Everybody can see that. Everybody can classify a galaxy based on the morphology. There was, I don't know if it's still active, a big project on the zoo, Galaxy Zoo, which asked people to just identify what type of galaxies. The types are elliptical, spirals, and irregular. And from the morphology, we already learned something about the galaxies. For example, ellipticals have essentially a big bulge. Spirals have, well, some more than others, but they have a bulge in the middle and then a disk with spiral arms around. And, well, irregular, of course, have no structure. Another thing is what type of stars are present in the galaxy. Yellowish, reddish light is an indication of old stars, and we find those in elliptical galaxies and in the bulge of spirals. While bluish stars are young stars, so we know that there is ongoing star formation, often also indicated by the presence of dust lanes. And star formation is usually found in the spiral arms of spiral galaxies and in irregular galaxies. Also, we know simply and also similarly to gas motion, that the stars have random motion in elliptical galaxies, essentially like a gas in a balloon, and in irregular galaxies, while spiral, apart from the bulge where there is, to some extent, there is random motion, then they follow a rotational motion. History, well, you probably know this very well. The first person that realized that galaxies weren't just nebulae in our galaxy, so in the Milky Way, but were in fact galaxies outside the Milky Way was Hubble in the early 20s. And he also classified them using this fork diagram into ellipticals, from roundies, from spherical ellipticals to squashed ellipticals, lenticulars, and then he divided the spirals into normal spirals and barred spirals. Based on this classification, we still today call the galaxies early type for the ellipticals and lenticular, and late type, which is a bit confusing because, of course, this name was given to them because Hubble and his friends thought that from an elliptical with a random motion, something started the rotation, and that would lead to a flattening of the formation of a disk, essentially, and then to the evolution of spiral arms. And so early type were early galaxies, then would evolve into flat spiral galaxies. So these names are still used in all papers, except this was absolutely the wrong interpretation. Important concept, again, you probably know about it. I just thought to make it clear, is the redshift. We define the distance of a galaxy based on the redshift. Redshift is a weird name because it's just, the name should be just shift, because it can be red or it can be blue. If the source that emits light moves away from us, then we have redshift. Otherwise, we've got a blue shift. In terms of a galaxy, or a star really, but a galaxy, we know where emission or absorption lines are in lab. We know at what wavelength they are. If the source is moving away from us, then this line would move towards the red end of the spectrum. If they're moving towards us, this line, and this is how we define redshift. In fact, mathematically is quite simply the wavelength observed minus the wavelength emitted over the wavelength emitted. And that's a natural number. So the redshift could be 1, could be 2, could be 30. In terms of galaxies and the universe, the concept is slightly more complicated because galaxies have a proper motion, meaning that they can move away or close to us. But what dominates in the universe is the expansion of the universe. So it's not the motion of the galaxy, it's the fact that the space-time fabric to which galaxies are attached, they're embedded into it, that expands. And so, like, if it's not exactly that, but as a concept, it's like galaxies are attached to the walls of a balloon, and as the balloons expand, the galaxies move away. Light that travels in space-time as well is also embedded in space-time. Then light gets stretched, and so if we stretch a wave, its wavelength increases, meaning that it becomes moving towards the red spectrum of the electromagnetic spectrum. Another important concept, just quickly to sum up all the little things that are part of galaxy evolution, is, well, because galaxies are made of stars, star formation and evolution is a fundamental part. Now, we know that stellar evolution is responsible for the formation of heavy elements. So initially we only had hydrogen, helium, and a tiny bit of lithium. And then in stars, we create heavy elements. Heavy elements, we also call it metallicity. Also, even if it's not just metals, it's all the heavier elements, but it's called metallicity. So stars with high metallicity are redder than the original stars made purely of hydrogen. And then, well, to form to form stars, we need gas and dust. These same things are also ejected into space when novae and supernovae happen. So it's a cycle of things. So even star formation is another important step to understand galaxy evolution. Another thing based on observation is what we call the luminosity function, mainly, which can be translated into the mass function because the two are linked. And this simply tells us that, well, we know it's a fact that in the universe there are lots of smaller or dimmer galaxies and not so many bright and very massive galaxies. Galaxies have contained medium, which is intergalactic medium. It was originally, as we said, hydrogen and helium mainly, and then metals come into play after stars evolve. Dust and gas are part of the galaxy, but sometimes, well, not sometimes, they're also present in a halo around the galaxy. They are ejected there by supernovae and other phenomena like starbursts, and then they fall back in. And while falling back in, they essentially replenish the fuel reserve for star formation. The density outside the galaxy is 1 atom per cubic meter. Active galactic nuclei, again, they are fundamental to understand how galaxies evolve. We know all galaxies have in the center a black hole, a supermassive black hole. Some are active, some are not. When they are active, they accrete matter, so whatever is in their vicinity. They heat the surrounding medium because they have jets that come out from the pole of the black hole. And heating the surrounding medium means that you push out gas and dust, and you stop the ones that it's out that would like to fall back into the galaxy. You stop it from cooling. So effectively, a very active AGN, so a very active central black hole, stops star formation. This picture is old now, but I think it's one of the best examples of what a black hole does. So we got an X-ray image that shows how hot the gas is, essentially. So we see where how far outside the poles of the galaxy the gas is. In the radio, we see the particles which are they're excited by the black hole and they emit in the radio band. And then we got the optical image, and if we superimpose the three, this is what we see, and we understand how the jets literally push out whatever could fall in the galaxy to form stars. And fundamental dark matter halo. So recently, we have observed some galaxies which don't have a dark matter halo as big as we expected, but the majority do. In fact, if you just look at the cartoon, the visible galaxy is tiny compared to the size of the dark matter halo. And how was this discovered? Because of course we can't see it. Well, one of the first evidence of it was measuring the speed, the rotational speed in spiral galaxy arms. So if we are in the center, and the rotation, the speed increases up to the edges of the visible galaxy. So mathematically, what we expect the further we go from the galaxy is that this velocity decreases. But in fact, it doesn't. Curve flattens, and in some examples, it uses this rotation to keep speeding, and we can't see the mass. Sometimes the mass of a galaxy, mainly the dark matter, is referred to as a gravitational potential well, because according to, in the way Einstein described space-time in general relativity and the gravitational force, essentially a mass deforms space-time, creating effectively a well, a dip, and every mass that goes close enough will fall into this dip, which is essentially the effect of gravitation. I will use this term to make sure that it's clear when I use it. Right, so a galaxy is a very complicated object. It's got the AGN, it's got things flowing out, things falling in, star forming, gas cooling, and so on, supernova, and so on. So it's very complicated. What makes it more complicated is that galaxies are not by themselves. They live in the universe, and the universe is big, and it's full, literally, it's filled with other galaxies. It's filled in a way that is homogeneous and uniform in every direction we look. So, of course, there seem to be less galaxies at higher redshift, but that's just because of the observational limitation. And also these lines are not real lines, they're due to the observations. But if we look, this is a real distribution, these are data. It's uniform, essentially, everywhere, in every direction. This is a simulation. This is a zoom in, and we see some clustering, but there isn't a preferential clustering in any point. Other problem, there aren't just galaxies in the universe. So the last satellite that was sent up to effectively measure the content of the universe using the cosmic microwave background was Planck. There was the Planck satellite. This is the image. The image essentially shows the density of matter at the time when the cosmic microwave background formed, which is very early stages in the age of the universe. And as we can see, the density is pretty much uniform. There are some overdensity, but bear in mind that these overdensity are of the type of 10 to the minus 5 in terms of the measures of the overdensity. So they are tiny. Even if it looks like this is more blue and this is more red, it's effectively it's uniform. Modeling this, we have as a result what is in the universe, and ordinary matter, luminous matter, or called baryonic matter, is a bit less than 5%. Okay, 5% is a very small number. We expect dark matter to be this much because we know that it's much more than the size of a luminous galaxy. But the real shock is the amount of dark energy. Dark energy is whatever is causing the universe to accelerate its expansion at the moment. Dark matter, quickly. Today, the best guess of what dark matter is what's called WIMP. So weakly interacting massive particles. Weakly, not because they interact weakly, but because they interact via the weak force, which is a type of nuclear force. The reason why this is the best guess is because of what we know. So we know we can't see it. So it's definitely not electromagnetic. Well, they don't emit electromagnetic radiation, so they're not baryonic matter. But not only this, they also don't interact with baryonic matter. Someone suggested in the past it could be antimatter because, you know, we've got lots of matter here. Maybe the rest is antimatter. But if it was, and because we know there is so much around a galaxy which is made of matter, then surely antimatter and matter would meet and annihilate, emitting X-rays. And we don't see any suggestion of that. Well, someone, again, in the past, suggested maybe it's black holes because we struggle to see them. Well, it's true, we don't see them, but especially now, we know how to observe them. For example, we know what they do to stars around them. So we can study the motions of other stars and X-rays emissions and so on. So we know where they are. So this is our guess so far. We, by this point, probably everybody expected to have some hint of these particles in the Large Hadron Collider. But no, there is nothing. They looked at the masses they thought they could have been, and there is nothing there. So it's open. Dark energy, well, I mean, we genuinely don't know anything about that. We know how much there is. It was discovered by observing supernova type 1a, and how the distant one, we thought they were moving at a steady pace following the expansion of the universe, but instead they are accelerating. So something is causing the universe to expand, accelerating, and this is whatever we call dark energy. Okay, so this is a brief history of the universe. This is where the cosmic microwave background that gave us the content started, which is 380,000 really years after the Big Bang. And then we got our expansion, galaxies here, galaxies today. And as you see, it's not going flat, but it's accelerating. Again, galaxies need to be considered in this in the universe and in its history. So Big Bang, then we've got matter, which is everywhere. It's created, as well as space, because space didn't exist before. And then, as I said, there were slightly denser regions where gravity was stronger, so it attracted more and more particles. And so big dark matter wells started to form. And roughly 1 billion years after, baryonic matter started falling into these wells. And so the first protogalactic clouds formed. As soon as the baryonic matter settled in the gravitational well, dust and gas started to cool down. And so the first generation of stars are born. We have never observed a first generation star. We think they're much more massive, we think they're super bright, but they have never actually been observed. And then massive galaxy formation starts at redshift 3 to 10, but galaxies to date have been observed at slightly higher redshift as well. And then galaxies, again, a bigger galaxy has more gravitational force, so it pulls a little one, and clusters and groups start forming, and so on, because of course the more mass, the stronger is the attractive force. And the new galaxies that encounter these big clusters or group start falling towards the center of them. This is a dark matter only simulation that describes the evolution of the structures in the universe. So at the beginning, it's roughly uniform, and then little clumps starts forming, and of course these clumps become bigger. This is a supercluster in the middle, and then we can see clusters inside and groups, and all of them are linked with filaments. So filaments are kind of a preferential lane for galaxies to fall into, or not, another cluster. We know that all the structures in the universe form via accretion and then merger. So smaller structures tend to fall in bigger structures. Of course, the merger rate declines as the universe ages. And this is because, of course, with the expansion, galaxies that are too far away to be attracted will be even further away. So we'll find ourselves in a universe with bound objects, which are clusters, with galaxies that are bound to each other, so they won't feel the expansion. But then the cluster nearby, which is too far, will become further and further from the other one. So this is what we expect to happen in the universe. As I said, groups and clusters start forming, and groups and clusters mainly works on groups. A galaxy does by itself. The fact that they live in groups and clusters is what causes really its evolution. This is one of the Higgson compact groups, which has, as you can count the big galaxies. And this is one of the Abel groups where there are way more galaxies. And this is a rough definition. A cluster has 50 and up galaxies and a size of 2 to 10 megaparsecs. But only 5% of galaxies live in clusters. Groups have usually less than 50 galaxies. They're smaller, but roughly half of all the galaxies in the unit are more interesting than clusters. So in clusters, big things happen, but there are more groups. Another thing, so this is a vague definition, and I just want to make clear that if you happen to read the paper, make sure that you read the definition, because everybody defines, especially groups, in a different way, which is based on what they want to do with it. So it's important to read the definition every time. A problem with clusters and groups, because I defined them, but they have edges. So if a galaxy is close, but it's really hard to tell if it's bound to the group or cluster already or not. So it's very difficult to define them. And also, if we zoom out, well, there's all the rest. There's filaments. And so galaxies in filament, are they part of the group or are they not? So this is the big picture. This is what we call the cosmic web, because it actually looks like a web. The main problem is the 3D structure. Now, if we observe, we have an almost exact 2D structure because we have right ascension and declination measured, done. We have a redshift as well that gives us the 3D structure. However, the redshift is much less accurate. So we don't have the same accuracy in the third dimension. But as you can see, these structures are not spheres. They're very complicated. So even to understand the motion of a galaxy in a structure with this shape, like the Hydra, for example, which is also joined to the Virgo and to A35A1, it's very, very complicated. We live in a group. It's got roughly 50 galaxies, mostly dwarf. So 50 galaxies would be the biggest size of a group. Sometimes though, excuse me, when we define it, we put a limiting magnitude. So let's say groups have a maximum of 50 galaxies above this magnitude. So ours is 50 galaxies, but they're mostly dwarfs. The center isn't a galaxy. It's between the Milky Way and Andromeda. And the diameter, again, is slightly bigger than what I told you before because it's 3 megaparsecs. The size, again, of a group is difficult to determine, even more than a cluster, because the gravitational potential well is shallower. And so it's hard to tell if a galaxy is really part of the group or not. Our group has a binary distribution, again, because it's split between 2 major galaxies. And we are part of the Virgo supercluster. So how do we observe galaxies? Well, you know the optical is probably better than me. In the optical, we look at stars. And we can measure the apparent magnitude, which is usually a positive number. The smaller it is, the dimmer the galaxy. We use filters. Of course, the apparent magnitude, though, it depends on the distance of the object. So in astrophysics, we don't use it at all. We use the absolute magnitude, which is for galaxies a negative number. But again, the smaller the value, the brighter the galaxy. As you can see, M87 is minus 22. The brightest known star is minus 10, and Sun and Sirius are above 0. Filters depend on what telescope you use. They can be narrower or wider in terms of the wavelength range they cover, but usually blue, green, and red light, roughly, and then we go in the infrared. We can also use the color, and we use that a lot instead of the magnitude, because difference between 2 magnitudes, for example, the B minus the V, the bigger the value, the redder is the galaxy. So the older, we can say, is the stellar population. And again, this is one of the plots that we like a lot when we study clusters. This is a color magnitude diagram. And this is what we call the red sequence, which has the ellipticals, usually, all the stars. We've got the blue clouds, which is young star. And the green valley, which is not very well defined, and it's a transition between them. We can also observe in UV and infrared, ultraviolet and infrared. So the UV shows the unobscured star formation. As you can see in this picture, the optical image, well, if you look carefully, might have some spiral arms, but they're not obvious. But when you look in the ultraviolet, you can definitely immediately see the spiral arms, and those are area of star formation. In the infrared, we see again star formation region, but those hidden by dust, because of course dust is heated by the young stars and it emits in the infrared. We observe in the X-ray. The X-rays shows us the hot gas. So usually the X-ray helps us to identify clusters. Some groups emit in the X-ray, but it's not all of them. But clusters definitely do, because the gravitational potential well has got so much gravitational force that the gas, that's the intergalactic gas, is heated to very high temperature and emits in the X-ray. We can also indirectly observe dark matter. And we do this by measuring the speed of the galaxy in a cluster, and so we can infer their mass, and from there the mass of the well, of the gravitational well, which is given mainly by dark matter. The best example is the bullet cluster, which everybody thought was one cluster, but it turns out to be, so the blue is X-ray, the red is mapping the dark matter, and it actually shows that the bullet cluster is two clusters colliding. Otherwise, the distribution of dark matter would be spherical-ish. Spectroscopy, again, I worked mainly on spectroscopy. It's less pretty, but it gives a lot more information. It studies the energy distribution in wavelength of frequency of the light emitted. Essentially is a prism, white light from the sun, a prism, and we've got a rainbow. This is the spectrum of the sun, which gives us the shape of a black body, and from that we can infer the temperature. As you can see, the sun peaks in the visible light, and then we can see that each wavelength corresponds to a visible color. Higher frequency, you know, means shorter wavelength, but a higher energy, and lower frequency, which is the red side of the spectrum, is a longer wavelength and lower energy. So when we look at the spectrum, what do we see? We see the continuum, as I said, the black body spectrum, and its temperature tells us where the peak, how high and where the peak is. A cold star will have a peak in the infrared, the sun in the visible. And we got absorptions and emission lines. So absorption is when we have a dip in our spectrum. Emission is when we have a spike. They all correspond to a wavelength, and we know because or emission, because at an atomic level, absorption happens when light arrives, hits an atom, an electron, which jumps up. So this because it's been absorbed. The electron jumps up a orbital, and when it jumps back down, it emits, usually at the same wavelength because the same jump. When we talk about astronomical source, we've got the source that shows us the spectrum. Hot gas, so gas that is heated by a luminous source emits, while if there is cold gas between the source and us, we see the lines which correspond to what the gas is made of. Galaxies are more complicated than that because the continuum, so the shape, the main shape, is the sum of all the star spectra continuum. The absorption lines, again, are some of the absorption lines, and they can be due to different things. They could be due to dust or, sorry, not dust really, heavy elements on the surface of a because inside the galaxy, but gas, stellar medium, the interstellar gas is ionized. What ionizes it is usually young stars or AGNs. So if I see a galaxy system like this, I already know there is an AGN because of the O3 and the H alpha line. Then we got a jump, which really is two jumps. One is the 4,000 angstrom break, which is due to cold, old, and metal-rich stars. And the other one is the Balmer break, which is at roughly 4,000 angstrom as well. So again, difficult to disentangle. But this time the Balmer break is not due to old stars, but is intermediate age stellar population. So this makes everything a bit more complicated. And the main downside of spectroscopy is the time of observation. If we want to observe a star or a galaxy anyway, the 20th magnitude, we would take 10 seconds in the V band for a good image, and 15,000 seconds to have a decent, probably not amazing spectrum. But all these things can be inferred from a spectrum, which we can't from an image. redshift. So we know, well, mainly the redshift is defined using known absorption lines. So I know where it is in lab, and based on where I observe it, we know how much it jumped in wavelength, and we can define the redshift. As you can see, the spectrum which we saw earlier with the 4,000 angstrom break, which should be here. This is redshift 3, so that's why it's so far away. They move towards the red, we said, ending up in the infrared section of the spectrum. The type of a galaxy. So even just by looking at the shape, I know that this spectrum is very boring. It doesn't have any emission line. It's got a big bump here. So this is an old galaxy. No star formation going on there. It increases, it gets a bit better. The jumps gets a bit more interesting. And here is where I start. Because the lines are a bit messy, and then we got AGNs. Galaxies are blue, and they're usually spirals, and red galaxies are passive, so no star formation ongoing, and they are usually ellipticals. From a spectrum using models, we can infer the key. So we fit with models, the main spectrum and the emission lines. And we, for example, in this, the top right, we see this, let's look one of these two, the bottom left, let's say. We see a red side and the blue side. So this is a spiral galaxy, not for the whole galaxy, but for one side of the spiral arm, for the center, and then for the other side. So on this side, we see that the lines are moving, is red because they're moving, they're redshifted. Of course, we need to subtract the actual motion of the galaxy itself. But in this side, they move towards the blue, which means that they're moving towards us. And so we know the direction of rotation of that galaxy. We can tell you how far it's moving because we can fit the absorption line, and depending on the width, we know how fast it's moving. And the gas density and temperature is given by the strength or intensity of the emission lines. Star formation history, again, using models, we can infer, not super accurately, the age, metallicity, and mass fraction of the stars in the galaxy. For example, at the bottom here, this shows us that this galaxy we are fitting here has, in the disk, the majority of stars, which is the bright yellow, have an age of 9 billion years. And the metallicity, which is higher than solar metallicity. Solar is 0. And in the bulge, we've got all the stars, but of the same metallicity, which makes sense because they're all the same galaxy. Of course, there are others. So you see that they're not just all there. The rest, there are some other populations, but the main populations are those two. This would be amazing if we could tell you that it's absolutely 100% accurate. But there is a thing, the main problem, which is the age metallicity degeneracy. So if you look here in this plot, there are two models. One of a young, the red one is a young stellar population, a young galaxy with high metallicity. And then we have an old galaxy with lower metallicity. So because the age, the lower age would make the galaxy bluer, but the metallicity makes it redder. The older age makes the galaxy redder, and the lower metallicity makes it bluer, which means that we don't know which one of the two it is. It's very difficult to disentangle these two. It's very difficult to improve this situation because of how complicated the galactic spectrum is and how many things are takes into account, how many processes are involved in this. So this is the main issue when studying spectroscopy. All that I've said so far applies very well to nearby galaxies. Nearby, let's say up to Redshift 1, maybe with the new telescopes 3 pushing it. But we want to look further away. We want to look where Hubble looked when it did the deep field first and then the ultra deep field. These, amazingly, were taken pointing at a patch of the sky where no other telescope could see anything. This is what Hubble saw. This is a few hundreds of millions of years after the Big Bang, corresponding to 5 to 10 billion light years away. And there's a lot of stuff, and there's a lot of interesting stuff, because immediately we see different shapes, different colors. So a lot is going on there. And of course, there is not also there, is also then, because those galaxies are not only far away, but they allow us to look back in time. Because, of course, light takes time to travel. It takes 8 minutes from the sun, roughly 4 years from the closest star, and billions of years from the furthest galaxies. So essentially, we are looking at those galaxies as they were billions of years ago. Problem with looking distant galaxies. I told you before how we infer the redshift and how the furthest the galaxy, the more the redshift goes towards the infrared. So we need big telescopes because these galaxies are dim and also sensitive to infrared light. So at some point, doesn't matter how good telescopes on Earth are or will be, they will be limited by the fact that they cannot get into the infrared. Also, as I said to you, we get redshift from spectroscopy. So how do we know that those galaxies are at high redshift, really? We need to prove it, but we know, but we need to prove it. Technique, spectroscopy is too long, especially not the dwarf. Different technique. Imaging is called the drop. Know where the jump is, the 4,000 angstrom break, for example. Galaxy in the H filter, we still see it in the J. We don't see it in Z, and we don't see it in the I and in the V. We need definitely 4 or 5 filters to make sure, because otherwise we could have just picking a very deep absorption line. And so when the galaxy disappears, it gives us a rough idea of where the 4,000 angstrom break is. And so we can have a redshift. So we have candidate high redshift galaxies that need to be confirmed using spectroscopy at that point. Another technique is gravitational lensing. Gravitational lensing causes these beautiful pictures with all the arches. So the galaxies are the deformed one are actually reaching in a straight line. Their light is bent by this mass, and so it's lensed and it's deformed, and also leads to the formation of more than one image for the same galaxy. So, for example, this red galaxy is the same as this one. But one of the main thing about gravitational lensing is that it's called lensing because actually the galaxies are magnified. Would have never seen that galaxy if the cluster wasn't in any way. They've been too dim, too far away. The photometry, if they look like they're far away, we do spectroscopy to confirm that the redshift is actually far away, well, a big redshift. Up to 2008, this was what we saw at high redshift, and it got to redshift 7 almost. This includes optical and radio observations, and also it includes galaxies and quasars. In 2012, we observed, well, Hubble observed what we thought was the furthest, well, what at the time was the furthest galaxy observed, which, as you can see, is invisible. But if you look close, this thing is an old galaxy at redshift 10.7. Originally, it was believed to be 11, and then it was confirmed 10.7. But the closest to date was observed in 2016 at redshift 11.1. As you can see, this image is pretty poor, so this gives an idea of how difficult it is to go any further. What we know, though, from even just the deep field, or the ultra deep field, is that galaxies in the past were bluer than today. This is yellow. They were brighter if compared to a galaxy of the same mass today, but overall they all had smaller masses. And also, because we said galaxies merge, they were more numerous. So there were more galaxies in the past than today. So this is what we observe, though. We observe our old galaxies, our young galaxy far away. We observe irregular, ellipticals, some weird spirals, red, weird galaxies. This is a red spiral. This is now an old paper. It's 41 years old, but it's one of the pillars of galaxy evolution. This is the morphology density relation. And is a very simple observation. If we look at a cluster, early type morphologies, so ellipticals and lenticular, are mainly found in dense environments, so towards the center of the cluster, while spirals are at low density. Again, if we want to talk about color, is the same. Redder galaxies are in the center, and blue galaxies are towards the outskirts of dense environments. The same observation can be done for the star formation. So the star formation is much less independently on the type of galaxy, is much less for galaxies that are in dense environments. So closer to the core of a cluster, there is almost no star formation ongoing. Another thing we observe is that we physically have been observing groups infalling into large clusters. So not only single galaxies can be attracted, but galaxies that already lived in group, which are medium density environments, are accreted all together until not long ago. It was red spiral galaxies. We thought spiral galaxies were star-forming galaxies by definition, but not all of them, and it's important to understand why. And this is why, because galaxies evolve. Says we start from the formation of a galaxy, and then we go internal evolution, which is what happens to a galaxy just aging. Environmental evolution, which depends on where the galaxy live. People of the same age have rougher life and age differently. Same for galaxies, and these are some of the mechanisms. Right, internal evolution. We briefly described it by talking about star formation and by talking about gas. So there is gas inside the galaxy and some gas that cools down from the halo outside. Supernova and AGNs push the gas out or stop it from cooling down. So effectively, they stop star formation. Intergalactic medium is enriched by supernovae with metals. And as a galaxy age, essentially by forming stars, it consumes the gas reservoir. And when it's all used, the star formation ceases, the stars just age, and the galaxy becomes redder and fainter. The morphology sometimes is part of the internal evolution because it has been observed an instability due to the presence of a bar in some of the spirals, which leads to the disruption of the spiral morphology and the evolution into a bulgy galaxy. This is not clear. It's not clear why it's happening, but it's one of the branches of galaxy evolution. And as I showed before, this is just internal evolution. But then it depends on where they live. If they are in a dense environment, they can interact with hot gas, which is there, heated by the gravitational potential well, or with each other. And those are the processes which I'm going to explain quickly. They go through. Ground pressure stripping is due to the hot gas. So essentially, when a galaxy falls into a gravitational potential well, there is a sort of a pressure, a friction almost, that the gas present in the, so the intra-cluster gas or intra-group gas strips away the gas from the galaxy. Of course, it depends on how fast. Friction depends on how fast an object is moving in a gas, for example. We can see in the picture, this is the same bubble, and we can see this lane literally lifted, but we know that the center of this cluster is down here. So lifted in the opposite direction of the infall direction. And the same in this case, where the contours are hydrogen lines, so taken in the radio. And again, this hydrogen gas is lifted in the opposite direction as the direction of infall. These leads to the disruption of the spiral arms, and so spiral galaxies become lenticular galaxies. Strangulation. Strangulation is when the galaxy is not disturbed, but the hot gas present in its halo, so around that's stripped away. If that's the fuel for galaxy formation. And so the galaxy keeps on evolving with the gas it's got inside, so it consumes all that, and then slowly it would just stop forming stars and becomes passive. And again, once all the gas is consumed, what this does is disrupts the spiral arms, and spirals become lenticulars. Harassment is when a high-speed galaxy encounters a group or a cluster. Usually this high-speed galaxy is a small galaxy, low luminosity, and it can interact either with a cluster, a group, or a bright galaxy. The point is that the galaxy that's speeding past is smaller in size, or much smaller in size, than whatever object it will interact with. This will disturb the morphology of the galaxy, could lead to the formation of a bar or just like a wonky shape. And because the gas can be compressed, it can lead to a starburst. Sometimes in this high-speed encounter, peripheral stars and gas are lost, and the stars would just roam in the intra-cluster medium. And this disrupts the morphology way more, and so spiral galaxies turn into dwarf ellipticals, because they dwarf, sometimes they even lose mass, so they become smaller. Tidal stripping is when two galaxies of roughly the same mass and at low speed encounter each other, and again, each other's gravitational pull deforms their morphology, often creating beautiful long tails. They're probably the best pictures of galaxies in the sky. The antenna galaxy is the most famous. Again, it can remove some stars, and it can remove intragalactic medium and intergalactic medium. So again, it will stop star formation because it can remove part of the fuel for it. But sometimes, depending on how this happens, some of the gas in some regions is compressed, and this ignites brief starbursts. Usually with tidal stripping, the galaxies go through a yo-yo effect, so they will pass each other and then come back until they eventually will merge. And of course, to merge, they have a low relative speed. What happens is that there is a complete disruption of the morphology, and especially the spiral arms. And because of the merger, the mass is essentially doubled, leading to the formation of a massive elliptical galaxies. This effectively is the mechanism that decreases the number of galaxies as the universe ages. In this case, again, especially during the merger, the medium, the galactic medium, can be compressed, triggering starburst. Usually not for long, though. One point to make about mergers is that galaxies merge, but actually very, very rarely anything, like for example stars, collide when two galaxies merge. Important to remember is that all these, whatever happens to a galaxy in a dense environment, let's say a cluster, it doesn't happen as soon as the galaxy enters that environment. So initially, a galaxy will always evolve following its internal processes, which start to consume some of the gas. And then whatever happens to the galaxy, again, starts from the outskirts. So star formation will stop on the outskirts first, because that's the easiest gas to strip off. Also, not all galaxies are the same. So not all galaxies are affected in the same way. It depends how big a galaxy is when she is accreted. It depends how big the host is. For example, if you're accreted by a group, you won't feel the same effects that when you accrete into a massive cluster. We know, we observe all of these processes ongoing because they all depend on different properties of the host and of the galaxy. But we don't know the strength of each one, especially is very difficult. You can't have a big picture for every galaxy because every galaxy is different. So we don't know their strength and their time scales. So if I see a galaxy entering a cluster, how long will it take until star formation is completely truncated? It's impossible at the moment to try and pinpoint. So this is what galaxy evolution is studying at the moment. This is where the research is going. Also, there is the epoch problem. So things that happen today didn't happen in the same way in the past. For common that galaxies encountered because the universe was smaller, so it was denser. However, the mass of all the galaxies were smaller, so the effect might have been smaller as well. So it's very, very difficult to have a clear picture. And this is, as I said, this is where the research is focusing at the moment. So essentially, galaxies and not and there are many. It's difficult enough for near, even more so for galaxies at high redshift. What we know is that the galaxy distribution in the universe follows the dark matter distribution. However, recently, as I said, we found galaxies that don't have as much dark matter as we expected. We know they have internal and environmental evolutionary processes. Internal, of course, mainly for massive galaxies, because they're more difficult to be disturbed, or galaxies that are isolated. And environmental are mainly affecting small galaxies, because they're easy to disturb morphologies and strip gas off. And also it happens mainly in high density environments. Round pressure stripping, strangulation and harassment are fast processes in terms of time scales. And so because of the high gravitational potential, they are more efficient in clusters, because galaxies tend to fall in clusters at higher speed. Slow processes like tidal stripping and mergers are more efficient in group, where galaxies are slower. And as I said, the evolution of galaxies in the past is one of the major challenges observationally of astrophysics. The hope is James Webb telescope, which was supposed to be launched early this year, but of course COVID disrupted him as well. And so it will be launched in October, and hopefully it will allow us to see the very first galaxies, because he's not only very powerful, so he can observe faint galaxies, but he's also got a good range in infrared. As I said, it will of course observe faint galaxies, so we might discover faint galaxies not so far. And because of the infrared capability, it will observe through dust clouds, allowing us to observe star formation regions, and why not, it will give us finally good pictures of extrasolar planets. And thank you.
Thank you very much, Melissa.
I hope it wasn't too boring.
It certainly wasn't. No, we lost the sound a little bit, I'm afraid, but your illustrations enabled continuity perfectly well. But some fantastic stuff regarding the evolution of galaxies, and I know that several of us are keen observers of galaxies. It does give us a new insight into it. I was out observing a couple of Messiers last night, and I wish I'd known all you've told us. So many thanks. So if we could probably unmute any in the audience and people who might like to ask a question or two. I mean, you only mentioned the James Webb telescope right at the end. Do you think if and when it does get up there and works well, it's going to be really revolutionary with regards to the evolution of galaxies?
Yes, I do, because so you will be able to observe the very first galaxies. We hope to observe the first generation of stars as well. And also the nearby galaxies will be observed much better. We might be able to do even more detailed spectroscopy, because as I said, because of the limitation of spectroscopy in terms of models, if we have a better, for example, if we can do finer spectroscopy for each region of the galaxy, that might really, really help. So it will be, I think it will be revolutionary in so many ways.
If it doesn't get up, what can happen? What's the best next instrument? Is it ALMA?
ALMA is in the radio though. So it's all the future is adaptive optics.
Ah, right.
And the only limitation of that is the infrared. That you need to go in space for that. Yes,
of course. Yeah.
But in terms of observation, I think someone suggested that some adaptive optics in South America will be almost as good as James Webb for local stuff.
Okay. Oh wow. Dave, can you unmute people, or can I unmute people?
They'll be able to unmute themselves if they've got a question, but don't unmute yourself unless you have a question.
Yeah, that's
Melissa, if you'd like to unshare your screen, that might help with your bandwidth a bit.
any of my lot have got a question, we got a couple of minutes if you have. Jens, you've unmuted. Does that mean you have a question?
Yeah, unless there are other questions. One of the things that determined the acceleration of the expansion was the ability to observe supernovas in high set galaxies. What's the current record for high set supernovas? Do you know?
No, I don't know.
think it was about 2, wasn't it?
Unfortunately, it doesn't look like the unsharing has helped with the bandwidth for Melissa.
No, it doesn't. No, it's frozen again.
Can you hear me?
Can now, yes.
Okay.
Yeah.
No, I'm afraid I don't know about supernovae that well. As I said, I was in a paper about them years ago, but I haven't followed the topic. So, but definitely being able to observe supernova 1A in further galaxies will help in understanding dark energy as well. So that will be a good step forward. Although I don't know if you read the article that came out recently about the Fermilab experiment, that they suggested they might have found a fifth force of nature.
Oh yeah.
Well, the G-2, yes. I think that
I mean, if that's true, that could mean a lot for astrophysics. So I don't know. I spoke to someone recently that works for the Large Hadron Collider. And I must admit, I don't know if it was jealousy. He didn't seem particularly excited by this news, because he literally said, oh, it's I don't recall which property of the muon, which is wrong at the 10th decimal digit.
Yeah, it's the G-2.
Yeah, so he wasn't particularly excited, but I don't know if it's because
well, the problem is with the theory is that the theory is extremely complicated, and you have to do a very high number of corrections to get to what you expect to observe.
Yeah.
And other forces could imply that you need further corrections, and that would then tie the experiment in with the observation.
Yeah. I mean, they weren't discovery levels yet, because they...
No.
So...
And they have...
Jens's.
Jens's dropped out now.
Yeah. The internet can be such fun, can be quite frustrating at times. Yeah. Okay. I don't know if we get Jens back at all.
His pictures appeared.
Yeah. Okay, well, you dropped out, Jens, there. I don't know.
Yeah, I think my internet connection is a bit wobbly.
A bit problematic all day. Let's blame the British weather, shall we? It's always good fun. Okay, well, I don't think there's anybody else having a question, but I don't think. But I'd like to thank you, Melissa, for your time and expertise and clearly great enthusiasm. It is a fascinating subject, and one that grabs us all, I think. It's interesting to see the developments, of course, and we're all keeping fingers, toes crossed that James Webb goes up, and we can start. I hope you're back working fully in your research capacity by then, have had your family completed anyway.
Yeah, definitely.
Melissa, thank you so much for joining us, and
thank you everybody.
We'll be in touch with an email. Just
okay. Thanks very much.
Thanks very much.
Bye.
Bye.
Okay, look forward to seeing everybody else for the telescopic topics on the 10th of May then. If anybody has a burning presentation, let me know. Otherwise, look forward to seeing you, and hopefully a few more in a month. So
I think I already sent a note that I've got probably around half an hour on the Arecibo telescope.
oh yes, that's going to be this telescopic topics, is it, Jens? Right, fine,
That's
lovely.
a very telescopic topic.
Yes, an X-telescopic topic. Yes,
Yes.
okay. Yeah, okay. Well, that's fantastic, Jens, and we'll probably a couple of other contributions. Keep it to about an hour and a quarter, something of that order. So nice to see you all, and look forward to seeing you in a month. And try and keep well. It's all looking much more promising now, isn't it? We'll get to a pub eventually as well after the meeting. So see you all soon. Bye all.
Cheers.
Bye-bye.